Hey guys, okay, so tonight we're going to be talking about some special properties of water. I'm going to be doing notes for you guys on page 87 of your interactive notebook. So that's where you're going to want to put this. And these are the special properties of water. Let's go ahead and write down our essential question. That would be, what properties of water make it a unique, universal solvent? Bunch of cool words in there that we're going to have to talk about. But first I want to talk about the structure of water, okay? Because you need to understand, and we did a little bit of this when we talked about covalent bonding. Water, of course, we all know is H2O. Okay, and if you draw the Lewis dot structure, we've got oxygen in the middle, a hydrogen on either side, and two lone pairs. Okay, now if I build that with my modeling kit, it doesn't end up looking like that. That looks like it's going to be a straight line. But really, these lone pairs on the top and the bottom make it bend like this. So I actually have an oxygen with two hydrogens kind of at a V-shaped angle. So I'm going to draw it a little bit more accurately over here. I've got oxygen bonded to hydrogens at sort of an angle. Now the really interesting thing about this is because of these two little pairs of electrons here, this end of our water molecule has a slightly negative charge. Not like negative like I took an electron, but slightly negative, just a little bit of negative charge. This other side down here where I've got the hydrogens, they're sharing their electrons with the oxygen, so they actually end up with a slightly positive side here. Okay, so water has a slightly negative side and a slightly positive side. We call this polar. Now, water is a very special kind of polar because the electronegativity of oxygen is so much greater than of hydrogen that this difference here, the difference between the negative side and the positive side is so great, it actually creates something that we call hydrogen bonding. What that means is that when this water molecule gets anywhere near another water molecule, my slightly positive end is going to be attracted to the slightly negative end of another water molecule. And if I keep adding these, my slightly positive end is going to be attracted to another slightly negative end. And I can keep on doing that, and every time I add another water molecule to this, the attraction is going to be the same. It's going to turn itself around so that the hydrogens of one water molecule are facing the negatively charged oxygen of another water molecule. The other thing that means is, let's say I have an ion. Like, let's say I have a positively charged sodium ion. My water molecules are going to be attracted to that because this has a slight little charge on it. So does this. This slight negative charge of my water is going to be attracted to this slightly positive side of my sodium. And so I'm going to end up with water molecules around this like this. So they're going to try to surround my sodium like this. And of course, they themselves need a little bit of a buffer between them. There we go. So I'm going to end up with all reds facing my sodium. Okay? So it's going to try to move itself so that the oxygen is closest to the sodium and the hydrogen side is the furthest away from the sodium. All right? And that's how we get things to dissolve. Okay? And that's why we say that water is a good solvent, because it is able to get things to dissolve. So it dissolves ionic things. It also will dissolve polar things, because a polar thing would also have a slightly negative and slightly positive side. So if I mix water with another liquid that's polar, it's going to mix with those two liquids. The only thing it won't dissolve is things that are nonpolar. So now this hydrogen bonding creates a really interesting phenomenon called surface tension. And I want you to imagine it for just a minute, like a big bag full of magnets, right? Okay, I got this big handful of magnets, okay, just like this, and they're all going to stick together. But the ones closest to the top are stuck together more tightly because they're only sticking to the other ones at the top. The ones below are spread out more. You have them attracted in more directions, but the ones on the top are only stuck to these two, and so the attraction is much greater and it's much more difficult to pull that off. And so that's why little water bugs are able to walk on the top of the water. It's because of that surface tension. When you were a little kid taking a bath, did you ever try to put your hands on the top of the water and see how they'd kind of float there on the top of the water, almost weightless? That's because if you do it just right, nice and flat, you can get your hands to float on that surface tension on the top of the water. Okay? And if you push your hands through the surface of the water, you'll notice that it takes more effort to break through the surface. And once you've broken through the surface, your hands will move through it much more quickly. Okay? That's why a belly flop hurts so bad, is because when you belly flop into the water, your skin has to break through that surface tension. Once you're under the water, it doesn't hurt as much anymore, but that first initial smack into the surface of the water hurts the most because of surface tension. The other thing that's interesting about water is that since it's sticky to itself, it has a property we call cohesion. Okay? Let me write out the word for you so you can see how that's spelled. Cohesion. Hesion is a word that means sticky, okay? Co means with itself. So cohesion means that it will stick to itself. Okay? So my water molecules, and you'll notice with these ones that I'm playing with, these models, they stick to themselves quite easily, in fact, and if I separate them, if I put them close together, they're going to jump onto each other and find a place to stick. They don't want to because I've got all oxygens or all hydrogens up. So there, I found a place to hook on. Okay, so they're going to try to stick together. These little water molecules want to stick together because they're very sticky because of cohesion. Let me show you what that looks like real quick. So I got a little piece of wax paper, and I'm going to put a couple of drops of water on here. And you'll notice this is coated with an oil that's nonpolar. And since it's nonpolar, our polar water does not stick to it. So my water actually kind of beads up nicely on it, and it'll just slide really well across this paper. But notice what happens when my water droplets get close to each other. They become one very quickly. And so all of a sudden my 4 drops become 1 drop. And again, they don't really want to stick to the wax paper because it's covered in a waxy oil that's nonpolar. Polar won't stick to nonpolar, but it will to polar. So I can do a whole bunch of these, and then I can make them all stick together. If I move this around, eventually they're going to join forces and become one big dripple drop. And I just rolled it right off. Okay, so that's cohesion. Another property of water is called adhesion. And that word should sound really familiar to you because you guys have played with adhesive tape. And that means that it sticks to other things. Glass, for example. Water sticks to glass really well. I'm sorry, I spelled that wrong. There we go. Adhesion. A-D-H-E-S-I-O-N. Adhesion. It means it's going to stick to other things. So for example, we talked earlier in the year about when you're measuring a liquid in a glass graduated cylinder, you have to be careful because it's going to be attracted to the sides of the glass because of adhesion. It's going to stick to the glass, and it creates that meniscus, that little bubble at the bottom. So I want to show you a little bit of adhesion with some of my saran wrap. Okay, it's a little piece of cellophane. Okay, this does not have a waxy coating like the wax paper does. And so this is going to stick more to my cellophane. You'll notice that instead of beating up like it did on the wax paper, that this kind of soaks in more to the cellophane. Okay? It's plastic, so the attraction is weak, but there's still definitely an attraction. And when I slide this off, you're going to see that water sticks to it. You can see those little water droplets that have stuck to the cellophane on there. So even though a lot of the water came off because of gravity, some of the water is going to stick. Whereas my wax paper, the water slid right off, and there is not really anything left of the water on my wax paper. So adhesion is where it's going to stick to things, and water sticks to a lot of things. Wax simply isn't one of them because it's nonpolar. Okay? One of the cool things about water is it's called the universal solvent because it's able to dissolve both ionic things and polar things. It'll dissolve more substances than any other substance in the world. Okay? And I want to show you just an example of this polar versus nonpolar conundrum. So in this beaker on the right, I have just some plain water. In this beaker on the left, I've got some acetone, which is a nonpolar solvent. Okay? So things that will dissolve in water will not dissolve in acetone. Things that will dissolve in acetone will not dissolve in water. So I have this styrofoam cup, and you might not know, this is a nonpolar substance. This is very much a long polymer chain of carbons, very nonpolar. And if I stick this in the water, as most of you probably expected, it floats pretty nicely. Okay? That is not the case with my acetone. You'll notice immediately that my acetone is going to eat right through my styrofoam cup. Okay? It actually can disrupt that polymer chain. And so when I scoop it out, I'm left with this white, gooey stuff. Okay? So, big difference between polar and nonpolar. Okay? Polar will not dissolve something nonpolar. Nonpolar will dissolve something nonpolar. So our styrofoam cup will dissolve quite readily in our beaker full of acetone. One thing that I think is really one of the most important things about water is its density. Okay? Water has a very special kind of density. And I'm going to use this to kind of show you because you actually already know this. You've observed it many times in your life. So I've got my water right here, and I'm going to show you in the liquid phase, I want you to look at how close together my particles can get. They're nice and close together, right? And they're going to constantly be moving around, sliding past each other. Okay? Now I want you to notice what happens if I slow down that energy. I let the energy kind of stop. And I let my water kind of take its own solid shape. Okay? So there my water has taken its solid shape. And I want you to notice that when my water has taken its solid shape, it's going to form little holes all the way through it. This space is going to fill with air in such a manner that it actually becomes less dense than the liquid form because the particles are actually further apart than they were in their liquid form. Okay? And that, ladies and gentlemen, is why ice floats on the top of water. When you put an ice cube into your glass of water, it stays at the top. Most solids would sink to the bottom if they were placed in a liquid version of themselves. But because of water's special properties, it's going to spread out. It's going to space itself out with these little holes for air. And so actually your solid water is filled with air that makes it float.